Thank you very much, Miklos. Thank you, Janos, for the talk earlier. And thank you all for coming for my second lecture. So this time I'm going to talk about Blackwell games. And this is going to be an application of the result that I've shown you yesterday on Borel games. So I have here two things that you can read. Probably there are more. One is the original paper of Martin from '98. And for those of you who have access to the draft of our book, or have somehow got a copy, it's chapter number 4. And actually this chapter, as I read it, I see that I would like to revise it. So maybe it's not such a good idea to read it in its current state, unless you want to help me to revise it. Okay, so let me start by describing what is a Blackwell game. So the main difference between the games that I talked about yesterday and these games is that these are simultaneous move games. The players play simultaneously. As you can see here, there are 2 players and they play simultaneously at discrete times. And the payoff, this is another difference, the payoff is not just 0 or 1, it's a function of the history, of the entire history of the game. And this function does not have to be, does not have to have only 2 values, it can have more than 2 values. And I will tell you something about some assumptions on this game. So we make some further assumptions. So at any position, if you look at the moves available for the players in that position, so now in each position both players move, so the available moves is a product set, moves for player 1 and for player 2, and we assume that these sets are finite. They have only finitely many moves at each position. This is one assumption. And the second assumption is that the payoff function is a Borel function and it is also bounded. So I think in the previous talk you've seen that in alternate move games, moving from a winning set to a payoff function, to a bounded Borel function, is not a big deal. It's a small reduction, but here it's more complicated, and in order to make the result general, we want to refer to general payoff functions and not just 0-1 functions. Okay, now I'm going to define formally what strategies are. This is very similar to what I did yesterday, but the difference is going to be that now I'm going to have mixed strategies or behavior strategies, which are randomized or probabilistic items, not just deterministic functions of the history. So a behavior strategy, or just a strategy of player 1, we denote it by sigma rather than S. It's a mapping that for each position it assigns a probability distribution over the available moves. So instead of taking one move at each position, it randomizes the next move. This is a behavior strategy. And if I have a pair of 2 behavior strategies, together they induce a random play or a probability measure over plays. And the payoff that we associate with these strategies is the expectation of the function f under this induced probability measure. Now I want to say what is the value that a certain strategy guarantees. So if I have a strategy for player 1, I look at the infimum of the payoff that it induces, where the infimum is over all strategies of player 2. And the value of a strategy of player 2 is the supremum of the induced payoff, where the supremum is taken over all strategies of player 1. So this is the value that a certain strategy can guarantee. Player 1 wants to maximize the payoff, and player 2 wants to minimize it, just as before.
Ron, you're assuming that in every step there are finitely many options, but is it bounded uniformly, or?
No, I don't need this assumption.
Okay.
Sometimes for notational reasons, sometimes people assume that the set of available moves is the same for every position. It makes the notation simpler, but for the result that I'm going to present, it doesn't matter. Now I have every game has two values, the min-max and the max-min. The min-max is the best thing that player 1 can guarantee, which is the supremum over players 1 strategies, the value of the supremum of the value of the strategies of player 1 over all the strategies of player 1. This is the best that player 1 can guarantee. And the max-min is the best that player 2 can guarantee, namely the infimal value of strategies of player 2 over all the strategies of player 2. And we say that the game has a value, or in Martin's terminology, we say that the game is determined if the two values, the min-max and the max-min, are equal. And if this is the case, we say that this quantity is the value of the game. Just one little thing to note is that the fact that there is a value does not mean that there are optimal strategies. It only means that there are epsilon optimal strategies for every epsilon. So this is what we are going to prove is this is a few words about the assumptions, but before that I will just say what the theorem says, and then I will state it more clearly soon. But the idea is that the Blackwell games do have a value under our assumptions, and now I want to show you a few words about the assumptions, not very deep things. First of all, why do we need mixed strategies or behavior strategies? Because otherwise there is no value. You can take the simplest one-stage game, such as matching pennies, and it already doesn't have a value with pure strategies. So there's no hope of getting a value with pure strategies. So we do need mixed strategies. And we do want the payoff function to be measurable, because if we use mixed strategies, then how can we define the payoff if the payoff function is not measurable? So maybe there are some clever ways to define it even if the function is not measurable, but just if we want it straightforward, we need some measurability assumption. And also, without the finiteness of the sets of available moves, we can also create a game with no value. We can even take a one-shot game. For example, the game in which two players choose an integer, and the winner is the one who chose the bigger integer. This is a one-stage game with an infinite set of possible moves, and this game does not have a value. Whatever one does, the other one can take a larger number. Yes?
Ron, can I ask just here, I understand this finiteness case. What about if there's some concept of compactness? Can you get something that will be similar?
Yes, maybe. I think that the answer is yes, but I have to think about it. What are the conditions? You need some conditions regarding measurability of some other measurability assumptions, which I cannot think about right now, but I believe that you can do something with the compact sets. You have to assume something about, I don't know right now, okay. Now, okay, this is the theorem. It says that Blackwell games have a value. When I say Blackwell games, I mean under the assumptions that I made, that the pair function is Borel and bounded, and there are only finitely many available moves. And this is what we're going to do today. I'm going to show you the proof. So the proof that I'm going to show you is very similar to the original proof of Martin, except for some elements that use martingales. Martin, although he's called Martin, he didn't use martingales. And I think that when you do use martingales, the proof becomes a bit simpler. But otherwise, it's very similar to the lines of the proof of Martin. So I'm going to use two preliminary tools. One is for Neumann's Minimax theorem. And this theorem says that if you have a two-person zero-sum game, a finite two-person zero-sum game, a one-shot game, then this game does have a value and the players have optimal strategies. So here you have the definition of a two-person zero-sum game, and this is the theorem that I assume that most of you are familiar with. So I will go to the next thing. So the next thing is Doob's martingale convergence theorem, or at least one version of Doob's martingale convergence theorem. The version that I will need.
Question.
Yes?
May I ask a question?
Yes.
I was a bit confused in the beginning when you were talking about simultaneous games, because I used to identify simultaneous games with one-shot games, and after what you have said so far, it seems like I was wrong. I made a mistake. So you're calling your games simultaneous because there are several moves, but in each move, both players play simultaneously, right? And that's not the same thing as a one-shot game. Is that right?
Yeah, so we actually call it simultaneous-move game, to say that each move is played simultaneously. But I think that since these games are of what is called perfect recall, we can view these games as one-shot games in which, in the beginning of the game, the players choose their strategies, and then the strategies induce a payoff. So you can have a sort of a normal form game, or strategic normal form game, that describe the same strategic situation.
Okay, but leaving aside any kind of transformations, at first sight, you would not say that a one-shot game is the same thing as a simultaneous game. No, they are different things, right?
A one-shot game is a simultaneous move game with a small interpretation. You can think of it as if they play in the first stage, and after the first stage, they only have one available action, and it goes on forever. If you want to turn it into a Blackwell game.
Okay, thank you very much.
Okay. Okay, so now what is the version of Doob's martingale theorem, convergence theorem that I'm going to use? Suppose I have a bounded super martingale or sub martingale. Then it is guaranteed that the martingale converges. It converges to a certain random variable, and it converges both almost surely and in L1. And if it's a super martingale, then the value of the limit is smaller than, the expectation of the limit is smaller than the expectation of x0. And if it's a sub-martingale, it's the other way around. Okay, is it okay to talk about super martingale and sub-martingales, or would you like me to define this notion? Okay, no. So we're fine. So I will need these two tools. Now the proof. So suppose we have a Blackwell game, TF. T is the tree of the game, and F is the pair function. And now I'm going to assume, without loss of generality, that F is between 0 and 1. So I know it is bounded. I can transform the game such that it's between 0 and 1. And the idea of the proof is that it is going to be a reduction to the result of Martin for alternate move games. Okay, so this is an auxiliary alternate move game that we're going to use throughout. So I'm not sure. Can you read this small font? Yeah.
Still can, yeah.
More or less. Okay. Okay, so this is how so actually it's a family of games. For every number u between 0 and 1, every positive number between 0 and 1, I'm going to have a game GU with a tree TU and a winning set AU. And this is the definition of the game. A play in TU it goes as follows. Player 1 chooses H1, which I'm going to tell you what it is, H0, sorry, and which I'm going to tell you what H0 is very soon. And then player 2 is going to choose A0 and then H1 and A1 and so on alternatingly. Now the choices of the moves of player 2 are tuples or are pairs of moves in the original game T. So in T, at each period, both players play. So now in this auxiliary game, player 2 is going to play both the action, the move of player 1 and 2. He's going to choose a pair of a strategy profile in every a move profile. And the HN are mini games. Okay, at any after any history, HN is going to be a mini game who's a mini two-player zero-sum game, a one-shot two-player zero-sum game, where the available the pure strategies of the players are the available moves after the history up to time n-1. Or I wrote it here formally. It is just a function, and we also assume that this function has values in the interval 0, 1. But we're going to have another important assumption, is that the value of the game, here I have a typo, it's the value of Vn, not of oh, sorry, it's correct. The value of the game of the game H0 must be at least U. U is the parameter of the game, and the value of I wrote here something. The value of the game at time n+1 is going to be at least the payoff that is given by the game at time n by the action profile AN. Okay, it might look a bit strange, but this is what it is. Can you, I'll give you a moment to digest what I've said, and if you want to ask me questions, because this is important, we have to keep in mind this game throughout the talk.
Not really clear what are the moves in HN and.
Okay, so player one, he chooses HN, he chooses zero-sum games. This is what he chooses. Every turn, he chooses a zero-sum game. And this zero-sum game, the action of the players in these zero-sum games are the moves available to the players, to both players, after the history A0 to AN-1. So at the first turn, HN is a zero-sum game where it's the first move of the game T, the first simultaneous move. And what player one here has to do, he has to assign numbers to the possible outcomes of the first move in the tree T. And these numbers define a two-person zero-sum game. Zero-sum game. Is it okay? Does it answer?
Yes.
Okay.
And sorry, in the second to last line, this h of A0 to AN-1 equals 0 implies. So what's the statement? Is there something missing? To the right of this implies arrow, or?
Just a second. Which line? Line number 4?
The second from the bottom.
So I didn't get there yet. Yes, it means implies, but I didn't get there yet. And yeah, I think maybe I have a typo there. But I didn't get there yet. Another thing that I didn't say, which you can see at the end of line number 4, is that HN of AN is greater than 0. So maybe I have to say what I mean by that. So the game follows like this. In the beginning, player 1 proposes a zero-sum game, and then player 2 chooses a profile of actions in that game, and they move on to the next stage. Then player 1 again proposes a zero-sum game, and player 2 chooses an action profile in that game, and so on. It goes on and on, but player 2 who chooses the action profile has to choose an action profile whose associated payoff is positive. Player 2 cannot choose an action profile that gives a payoff 0. Okay, this is a restriction on player 2. And the restriction on player 1 is that the value of the game must be at least the payoff that was attained in the previous round. Okay, in each round they choose a game and then a profile. So the profile defines a payoff, attains a payoff. And then in the next game, the value of the game must be at least the payoff that was attained previously. Okay, so we have to think a few minutes just to see that this is indeed a game. This is indeed a tree. Namely that every position has an extension, and every prefix of a position is a position. So there is no problem with prefixes. We only have to say why there is an extension. So for player 1, there is no problem to extend. Player 1 can always play the game in which everything gets 1. It gives high enough payoff. And since we assume that the value of the games that player 1 chooses are positive, then player 2 can always find a profile for which the payoff is positive. If the value is positive, then there must be at least one profile that gives a positive payoff. So this game is indeed well defined. The tree of the game is well defined. It's a tree. And now the winning set. The winning set is the following set. If we look at Hn of An, namely the payoffs attained during this process, the lim sup of these payoffs must be at most the value of f at the induced play. Okay, so it means that player 1, in order to win, player 1 have to be careful when player 1 chooses the games. Player 1 should not choose too high payoffs. If player 1 can easily find an action in which all the payoffs are very high, but this is not good for player 1 because then the lim sup will be larger than f. Okay, so it places a challenge for player 1. Now I'm going to look at the strategy. Now this is a note, and I think I have a typo there, but I will try to explain it and correct the typo maybe. So the set of strategies of player 1 have the following description, or they are isomorphic, or there is a natural correspondence between the strategies of player 1 and the following set. The set of functions from the positions in T to 0, 1, such that the empty position gets the value u.
U or at least u?
Sorry?
U?
Yeah, u, exactly u.
Okay.
At any position, if I look at the continuation payoff, at any position of T, I can consider a game in which the players play for the payoff of the next round. So the value of this game must be at least h of that position, the value of h at that position. So once I reach a position with a certain value, in order to proceed to the next round, this step is a zero-sum game whose value is at least the current value. And if for some position the value is 0, h is 0, then in the following positions the value will also be 0. So this is what I miss here. Maybe I can try to write here. Here it should be equal 0. So this arrow here is implied, and it means that if at some position up to time n-1 the value of h is 0, then any extension of that position is also 0. So we can think about h as some sort of continuation payoffs, or something like that. Once you reach a certain stage of the game, I don't know, you can give it any interpretation you want, but you can see that the strategy of player 2 induces such a function and vice versa. Okay, such a function defines zero-sum games in a natural way, and also the other way around. If you have zero-sum games, you know what is the relation between one step to the other. You can somehow, it's a natural correspondence. You just follow these HNs. Okay? And the places where H is 0, these are exactly the positions which are not legal in the auxiliary game. You are not allowed to move to a position where you get 0. This is not an allowed step for player 2. So we just set all these to be 0. Okay. Now I'm going to continue. So it's important to have this game in mind. Okay. Okay. Now, as I said, there is a certain parameter u, and I'm going to show you that there is a certain critical u, which is going to be the value of the game, of the Blackwell game. So the first, the reduction step is to say that the GU is an alternate move game, and it follows all the rules of Martin, so it is determined. The only thing you have to think about is why the winning set is a Borel set, but f is a Borel function, and lim sup is also a Borel function, so the difference is a Borel function, and the fact that one is greater than the other is a Borel set. Okay. So GU is determined. This is a crucial step. And now if you take U and U prime, U larger than U prime, you just compare these two games, the trees of the game. So TU for the larger U is a one imposed subtree of TU prime. Actually, the only difference is in the first move. After the first move, they have exactly the same rules. In the first move, player 1 must propose a game whose value is greater than U. So if U is greater than U prime, then in TU, player 1 has fewer options than in TU prime. So this is a one imposed subtree, and furthermore, the winning sets have the same condition. Okay, so formally, AU is just, if U is larger than U prime, AU is the set of all plays in TU intersection with AU prime. Okay, so essentially what this means is that if player 1 had a winning strategy in GU, then player 1 has a winning strategy in GU prime as well, because you only allow player 1 more strategies. And therefore there exists a critical U prime such that above that, a critical U star, above U star, player 2 wins, and below U star, player 1 wins. Okay? Okay, so I'm going to show you that U prime is the value of the original game, of gamma, of the Blackwell game. And in order to do that, I have to prove two lemmas. The first lemma says that if player 1 wins GU, then player 1 has a behavior strategy in gamma, in the Blackwell game, whose value is at least U. So when I'm below the critical U star, player 1 wins not only in GU, but also has a strategy in gamma that gives player 1 at least U. And when I'm above, if player 2 wins GU, then for every delta greater than 0, player 2 has a behavior strategy in gamma whose value is at most U plus delta. Okay, so player 2 wants to minimize the payoff. I cannot show you that player 1 can guarantee U, but can guarantee anything slightly bigger than U. So these two lemma, if I prove these two lemma, it concludes the proof, right? Okay, we're fine with that? Okay. So now I'm going to prove the first lemma, lemma 1. I'm going to show you how player 1 wins. I'm going to assume that player 1 wins GU, and I'm going to construct a behavior strategy for player 1 in the Blackwell game. So let's say that S1 is a winning strategy in GU for player 1. And now you can remember that any strategy can be identified with a function that assigns numbers to positions in 2. This function h that assigns numbers to positions such that from any position, the game playing in this position and getting the payoffs in the next position has a value greater than the current value of h. And also once it gets 0, it stays 0. And in the beginning, it is u in the empty position. So this is this function corresponds with the strategy of player 1. Now we define sigma 1 in a natural way. Sigma 1 at position P is going to be optimal strategy in the game that the function h defines at position P. So suppose we're in position P, I look at the function h, and I want player 1 to play an optimal strategy in the game whose payoff is the next value of h. Okay? Now I'm going to I want to show you this sigma 1. Actually, the value of this sigma 1 is at least u, right? So this is how it is done. You just take an arbitrary strategy for player 2, and together with the strategy of player 1, with sigma 1, they induce a probability measure over plays. And now we define the random variable xn to be just the value of the function h at the history of length n. So h0 is going to be, what is going to be? I just want to see that you follow. What is x0? Okay, just I can go back a little bit. Okay, I have plenty of time. No, back. Okay, what? So remember, xn is the value of h at the history of length n. And so what is what is x0? You have here a clue?
U.
U, right. Very good, Miklos. So x0 is u, and what is x1?
So we have fixed some strategy of the opponent, or yeah. So I mean, it's probably like the average of h when sigma 1 and sigma 2 play.
Yes, and sigma 1 is an optimal strategy in that game, right?
Yeah.
So at least the expectation of, what can you say about the expectation of x1?
So u is yeah, I mean, it should be smaller than, smaller or equal to the value, right?
Larger than the value, because player 1 is the maximizer.
Yeah. I mean, so it's larger than u, I guess. Yeah.
Yeah. So the expectation of x1 is larger than x0, and you can continue like this. So what you get, the x1, x2 are a sub-martingale. Okay. At any position, the expectation of the next round, conditioned on the previous round, is larger or equal than the value of the previous round. So it's a sub-martingale, and it's bounded because it's bounded between 0 and 1. So by Doob's theorem, we know that it converges to something, to some x. And we also know that the value at the limit, namely x, the expectation of x, is larger or equal than the expectation of x0, which is u, as Miklos said. So we have this inequality, u is less than or equal the expectation of x. And in addition, now we're going to use the fact that S1 was a winning strategy. What does it mean that X1 was a winning strategy? It means that if the play, now we have to go back to the definition of the game. Recall the definition of the game. In this auxiliary game, we had this sequence of A0, A1, and so on, but in between there were H1, H2. So if this play x0, x1, so on, is consistent with the auxiliary games. Namely, you can find h1, h2 such that the whole thing is consistent with s1. Okay? Then, since s1 is winning, we know that the lim sup of x, the lim sup of xn, which is equal to the lim of xn, is less than or equal f, because this is the winning condition of the game. We know that s1 is winning. But if it's not consistent, then it means that at some point xn got to 0. So the function h got to 0, and by definition, from that point on, h stays 0. So if the play is not consistent with the auxiliary game, then we know that x is 0. And since f is larger or equal 0, then in any case, for any history, we have that x is less than or equal h. So if we plug in these inequalities together, we get that the expectation of f is larger or equal u, which is what we wanted to prove, right? We wanted to prove that the strategy sigma 1 guarantees a payoff of u. Okay? Okay. Arkady, you don't look happy. Okay, I think I have plenty of time. I can take questions, I can explain this, because the other side of the proof is similar but a bit more complicated.
Do you have a toy example of this construction?
I don't have, but I can try to draw one right now. So let me try to think how to draw an example. So this is the tree of the game. So it's more complicated than that, because the players have in each round of the auxiliary game, a move is a strategy pair, so I cannot draw it with a binary tree. So what player 1 actually does is it assigns numbers here. Let's say 0.1, and then 0.2, and here 0.3, and here you might have 0.112, 0.3, but overall these numbers increase. They don't have to increase in every step, but if you look at, if you start here at this position here, and you play this game to the next position, then the value should be greater than 0.0. If you start here at this position. So on average, it should increase. That's the idea. I don't know if it makes things clear. I didn't prepare any example that really that I gave a thought about.
Ron, I'm sorry if I gave the impression that I am unhappy. I'm just a grumpy old man. That's it.
No, sorry.
What I could maybe say is that it's not easy to construct an example, but maybe just a piece of intuition that I have. It's as bad as any piece of intuition you could imagine. But I always think of player one's strategy as a kind of a promise of a continuation value, a promise of a continuation value. So player one basically initially says, okay, so if player two chooses this action profile, then the continuation value will be this. And if a player two chooses another, then it will be that. And every time player one is supposed to keep the promise at every step, in the sense that if she said that after action one, the continuation value will be 0.2, then in the corresponding one-shot game, when we reach it, its value has to be at least 0.2. So this is effectively the martingale condition. And then the winning condition basically is that the sequence of this continuation value is somehow justified in the sense that it's not greater when we finish the game, when everything has been played and everything has been said and all the promises have been made, then in the end we see that the limit of the promises should not be larger than the actual payoff on the realized play that player two constructed. Okay, so I'm sorry for this interruption. I was just thinking
about that's very good. That's a very good interpretation. I like it. So player one makes promises, and in the end, player one has to pay the promise, and the only way for player one to pay it is to pay it from F. So if he can pay it from F, then it's okay. But if not, then player one loses. And player two, on the other hand, he wants to show that the promises are not reliable. So player two chooses action profiles. He never wants to get to 0, because from 0 you can continue to 0 forever. And and somehow wants to show that the values go too steeply up. Okay, so thank you, Arkady, for the interpretation. So now I will move on to the proof of the second lemma, which, as I said, is a bit more complicated, but has a similar flavor. So now we assume that player 2 has the winning strategy in GU. So let's say that S2 is the winning, is an optimal strategy, or it's a winning strategy for player 2. And we construct sigma 2, whose value should be at most U plus delta for some positive delta. And we're going to define several objects recursively and simultaneously. So it's a bit tricky. What can I do? Martin is a clever guy. His proofs are tricky. So I'm going to define here several objects simultaneously and recursively. So the first thing I'm going to define is a subtree of T, which the positions of its T prime, and the positions of T primes, they are called acceptable positions. So I'm going to say that some positions are acceptable and some are not acceptable, and this is all with respect to this S2, to the strategy. It depends on the strategy S2. And the rules are as follows, and also I'm going to define another object for an acceptable position. I'm going to define a sequence of moves of player 1. So we are in the head of player 2. So player 2 has to imagine some moves in the auxiliary game, because they don't play the auxiliary game. They actually play the game, the Blackwell game, but in order to use S2, player 2 needs to imagine something happening in the auxiliary game. So we say that for every acceptable position, player 2 will be able to find some h0 to hn minus 1, some moves of player 1 in the auxiliary game, such that the resulting position in the auxiliary game is consistent with S2. Okay? And these h0 to, I wrote the vector sign above the h instead of above the a's. But what I meant is that these h0 to hn minus 1 are also defined recursively, okay, for every acceptable position. And also we are going to define a function h as, or similarly to the one that we had before, some, as Arkady said, some promise, but now it's a promise of player 2. So in the beginning, for the empty history, it's going to be u, and at any position, at any consistent position, I'm going to use the little h's in order to define. So I have here another typo. Let me correct. Okay, so here it should be n minus 1. H of n minus 1 of an minus 1. So if I have an acceptable position in the Blackwell game, I can find a consistent position in the auxiliary game, and I use the hn minus 1 of that position to define the promise of that position. This is the promise of that position according to the consistent history. And if it's not in T prime, if it's not acceptable, so it's out of the game, you cannot get there in the auxiliary game, then I just give it 1. 1 is the worst thing for player 2. Player 2 is a minimizer, he doesn't want 1, so I just give it 1. So this is sort of what the player 2 is trying to achieve. These are the continuation payoff, or the promises that player 2 wants to achieve. Okay. Now I'm going to define zero-sum games as follows. For every position in the Blackwell game, I define a zero-sum game. This is the game that is played at position P and whose payoffs are the continuation payoffs. And the idea of this game is that the value of the game is smaller than the current value of h. So unlike the promise that player 1 made to be larger than the current value, now this game u gives me something smaller than the current value. And if I look at the continuation value, h of a0 to an, not n minus 1, then it's going to be smaller or equal than what the game gave me at that continuation move, plus a small error term, delta times 2 to minus n. Okay, now I think I think I got the inequalities in the right direction. So the first one, I'm sure. The second one, I hope it's correct. It's the value that you get, the value that you assign to yeah, there is only a small difference between, so what is the difference between U and H? H corresponds to the promises that player 1 made, to this small h. Okay, so player 1 wants to be optimistic, wants to give high payoffs, because he wants the value to be higher than the current value. U wants to be low. It wants the value to be smaller than the current value. So U is a bit smaller than H, but not much smaller. That's what the second inequality says. That U is not much smaller than H. There is a small error term between them. And now we define sigma 2, the behavior strategy of player 2 in the Blackwell game, to be in every position. It's going to be an optimal strategy for player 2 in the one-shot game UP. Okay, so in any position I have this auxiliary one-shot game UP, and UP is not much different than the promise of player 1 H, but it is enough, it is slightly smaller such that the value that it gives me is less than or equal the current value. Now I take an arbitrary strategy, behavior strategy for player 1 in the Blackwell game, and these induce a play, and I look at the random variables yn. Yn are going to be just the value of h, just the promise of, as before, the promise that player, the promise of player 1 in the auxiliary game, which is h of this value, plus something small, delta times 2 to minus n. Okay, and this something small shrinks and shrinks. And the point is that yn is a bounded supermartingale. Okay, so the idea, why is it a bounded supermartingale? The idea is that sigma 1 is an optimal strategy. So it in expectation it gives the value, and the value of U is smaller than H. But and in addition, the payoffs that you get with U are not much bigger than the payoff you get with H. Okay, and Y is defined in terms of H. So this, if you just write it, you have to write it on a piece of paper. You see that everything cancels out, and you get the inequality in the correct direction, and you get that Yn is a supermartingale. It decreases, and since it's bounded, it converges, and as before, the expectation of y is less than or equal to the expectation of y0, and if you just ask yourself what y0 is, so y0 is, as before, it is u, but also with the error term, because y is defined as h plus something, and when you plug in n equals 0, you get delta. So it's y plus delta, but this is why we want to show that, that y is greater than f, and this is indeed the case, because as 2 is a winning strategy. So if I take a history, and let's say that the history is acceptable, all the prefixes of the history are acceptable, so it means that this history induces a history in the auxiliary game, and the history in the auxiliary game is consistent with S2, and S2 is a winning strategy, so the limit of the H of these histories are smaller than the limit of these H is smaller than F, because this is the winning condition, and the arrow term shrinks to 0, so it doesn't matter for the limit. So we have that Y is greater than F, and if the play is not acceptable, so when it becomes unacceptable, then Y becomes 1, or not Y, H of that value is 1. This is how we define the U, and we get that H is 1 from that point on, and therefore in this case too, Y is greater than F, because F is bounded by 1. So when we plug in the two inequalities, we get that sigma 2 indeed guarantees U plus delta. So maybe it's a bit confusing, but this is something that you just have to write down to yourselves, and you see that the things cancel out. But this idea of taking the continuation payoffs, this is the main idea, and then you can try to find the martingale. That's the game. Okay, now I have time for questions, and then I have something else that I can say. So I can take questions now. Yes, Abraham?
Yes.
Do you have a question?
Hello?
I saw that you...
Yes, I'm sorry that I was on and off the lecture. So can you bring the slide with the theorem? It's more a comment than a question, but...
No. Okay. Yeah, this one?
Yes, but do you have here the definition of Blackwell games? Or did you focus on stochastic games?
So I have another slide on stochastic games, if this is the...
Yes.
Okay, so this is a brilliant question, because I do have
what was the payoff of the Blackwell game?
The payoff of the Blackwell game was a bounded Borel function.
A bounded Borel function. And did you talk about stochastic games? So
no, but I do have a slide about it.
Okay, no. So then my comment would have been that sometimes there are natural functions F that are assigned to some games, like in stochastic games, and in those cases there is another function that so there is the upper F and the lower F, like the lim sup and the lim inf of averages of payoffs, and then it is of interest to find when it means when the value with respect to the lim in function of the averages is equal to the value of the lim sup of the averages. But if you didn't talk on stochastic games, then it's... So
maybe I have here a slide. So I just want to say that this result that I've shown you, it extends to stochastic games. And what do I mean by stochastic games? These are, so it's in a sense, it's a general definition of stochastic games, but also less general than the notions that, for example, Peretz and Neumann proved, for the uniform value. So it's in a sense it's more general, but it's also less general. So a stochastic game in this setting is a game as before. We have player 1 and 2, but we also have nature. And in player 1 and 2, they play simultaneously, and then nature makes a move. And as before, we assume that everything is finite. The set of moves are finite. And but the difference between nature and a player is that the behavior strategy of nature is fixed. It's part of the description of the game. It's a parameter of the game. So at any given history, nature just plays a mixed strategy, which is well known to everyone in advance. So this is the setting, and then the payoff again is a function of the entire history of the moves of player 1, 2, and nature. And it's a bounded Borel function, and these games too have a value, and the proof is very similar. It's a small modification of the proof that I've shown you. The modification, it's a very small modification. You construct the same auxiliary game, but only now you have, instead of player 2 playing for the 2 players, player 2 plays for the 2 players and nature, and player 1 still assigns continuation values, but when you consider the value of the continuation games, it has to take into account that nature is not a player, but only a randomization device. So this is just in the notion of value, but otherwise the whole proof follows through with very small changes. So it actually proves that stochastic games have value, but not in the sense of Mertens-Neumann. It's not a uniform value. You need a well-defined payoff function, and only with respect to that function you can say that the game has a value. Okay.
Another question for clarification.
Yes.
It's okay. So just to go back to this construction, at which step exactly are you using the fact that delta is strictly greater than 0?
Oh, okay. Maybe I skipped something. Yeah, I think I skipped something.
You kind of glossed over it, I think.
I didn't show you how to construct. I was so puzzled with no one asking questions that I just skipped to the end. But yes, it's not the end of the proof. Actually, I didn't show you how to define this U and this H, right? I said I'm going to define something recursively, but I didn't.
That's right. Yeah. No, you didn't do it wrong.
I spared you some something. So now, Richard, you really forced me to show the whole proof. But the place where you need it is to show that you can construct this continuation pair of U, this auxiliary game U.
But it exists, in fact.
That you can construct. So I didn't do it. I don't know if I should do it. What do you say, Miklos? You're the organizer. Should I show the remaining part of the proofs that I skipped?
I vote for yes, but of course this is a very democratic training school, especially some privileges to the speakers. So you do what you want, but.
Okay, so I'm going to. Well, I have to do it. If Miklos says it's one man's vote. So I didn't do it. So I have to define all these objects, these acceptable positions, and the function U, and the imaginary moves of player 1, the H's, all this. So this is how it is done, So if P is not acceptable, is unacceptable, then any extension of P is also unacceptable. That's the first rule in the definition. The second rule is that the empty position is acceptable. Otherwise, it wouldn't be interesting. So the first position is acceptable. And now suppose it's a recursive definition. So suppose I have an acceptable position of length n, a0 to an minus 1. And for that position, I've already defined h0 to hn minus 1. These are already defined by the recursive. In particular, it is well defined for the empty position, because then I don't have to define any h. An extension of this position, a0 to an, now I have n plus 1 elements, is acceptable if and only if there exists an h such that I can put it in this history so that it is consistent with S2. So if I can somehow complete it into a history of the auxiliary gain that makes it consistent with S2, then I say that the history of length n plus 1 is also acceptable. Okay?
Can I ask something?
Yes.
So this notion of acceptable, it seems to depend on the h0 to hn minus 1 that you've already chosen. So
that's true. That's true. This is the point that I wanted to say next.
Okay, sorry.
It depends on the choices that I made already. So it might be the case that I can somehow find other h0 to h something, but I'm already committed to h0 to hn minus 1. So I must be able to find a new h and extend it to the existing h's. Okay, that's the condition for position.
So this notion of something being acceptable is not an absolute thing. It depends on the steps that you made earlier.
Yes, so I have some freedom in the definition, and it's also a recursive construction. Yes, I have some freedom. It depends on the choices that I made before, and I will have some freedom regarding these choices.
Okay.
Now I denote by Q of the history of length n plus 1 the set of all possible h's. So I have some freedom to choose this h. I know that such an h exists, but there are several such h's. So I have a certain notation Q for the set of all these possible h's. And now I define the gain, the auxiliary one-shot gain U at the position of length n minus 1, but remember, a gain gives a number to each continuation. So at this specific continuation, an, it's going to be the infimum over all the possible h's. Okay, so there are different possible h's. If I take, and each such h gives a different number to the move an, and I take the infimum over all such h's. This is going to be U. And if this set is empty, if Q is empty, or in other words, if A0 to AN is not acceptable, then I define U to be 1. The worst thing for player 2. This is the definition of U. And now I have to define, now I want to commit to Hn. Okay, I haven't committed yet to Hn. I know that there is an H that will make things work, but I want to commit to one such Hn. So I commit to an Hn in Q such that Hn of An is not much larger than U. U is the infimum over all such H's. I don't know that the infimum is a minimum. If it was a minimum, I would take the minimum. But I don't know that a minimum exists, so I take the infimum over all, I take an h that is close to the infimum. It is delta plus, it is delta times 2 to minus n away from the infimum. Okay, this is how and here I have some freedom to choose hn, but I choose one of them and I commit to it from that point on. And then I continue the construction by induction. Okay, now I have to verify, if you recall from the list of conditions that I needed for the proof, one of them was that the value of this game u at any position p is smaller than h of p, than the promise of player 1, according to the imaginary history. Okay, according to the imaginary history, the promise of player 1 is h of p. And I want to show that the value of u of p is smaller than that. This will give me the super martingale condition. Okay, so how do I do it? If p is unacceptable, then both hand sides here are 1. Because u is defined to be identically 1, so the value is 1. And h is also defined in a way that unacceptable histories get the value 1. So if it's unacceptable, then it's 1 on both hand sides. So let's say that I have an acceptable history of length n, but for the sake of a contradiction, I have that the value of u at this position is equal to h of p plus epsilon for some positive epsilon. And h of p is just, by definition, it is hn minus 1 of an minus 1. So it's the promise that player 1 made at time n. Okay, this is h of p. Okay, so I have this, I know that the value is, it is the promise plus epsilon. Now I can define a game h, a game at position p, a one-shot game at position p as follows. I take u minus epsilon, but if it becomes negative, I just round it up to 0. Okay, so it's the maximum between 0 and u of that action profile. Okay, so it is something h is a bit smaller than u, right? I take u minus epsilon. But the point is that, see, the point is that okay, h is smaller than u, but it is bigger than u minus epsilon, because it's u minus epsilon, but rounded up when it's negative. And therefore, the value of h is larger or equal to the value of u minus epsilon. But recall that the value of u minus epsilon is exactly the promise, the hn of an. Okay, this means that h is a possible move for player 1 in the auxiliary game at the position, the imaginary position that player 2 had in his mind. So if player 2 had in his mind a certain imaginary position in the auxiliary game that contains also the h's, and in that position, this h that I've just defined is a possible move for player 1. Okay? And not only is it a possible move for player 1, we also know that the response of player 2 is going to be an action, an plus 1, such that h of an, so I have several typos here. See? Oh. This should be an arrow here, and this is an. So h of an has to be positive, because this is part of the rules of the auxiliary game. The player one can only take moves that lead to positive promises. But if HAN is positive, then it means that HN is equal to U minus epsilon, right? Because the only way I can get to positive values in H is if I took, remember that H is just U minus epsilon, rounded up to 0. So if H is positive, it means that H is U minus epsilon, but this is a contradiction to the definition of U. If you recall the definition of U, it was the infimum over all H's. So I cannot have an H that gives me something smaller than the infimum. Okay, I know this part of the proof is a bit tricky, but this is, I think, the only reason why Martin chose the moves of player 2 in the auxiliary game to be such that player 2 must move to a position where the promised payoff at that position is positive, just in order to get this contradiction here. Okay, so this proves that the value, and I think this, if you look at all, I don't think I missed. Now I think I gave the entire proof. So if you look at all the conditions that I promised you that will be satisfied, I think now they are satisfied. Okay, so I'm done. Thank you very much.
Thank you, Ron. Questions, remarks?
I have one remark, but actually it's just showing my ignorance about the whole thing. Whenever I was thinking about simultaneous move games, I always thought that they are just extremely different for games with alternating moves. And so I find this proof by Martin completely contradictory to my own naive imagination, because it shows that somehow you can translate a simultaneous move game into an alternating move game. And even though I read the proof, I still don't fully understand how on the planet this is possible. So to me, this is one of the most amazing, but it's just my own very, don't pay too much attention. To me, it's one of the most amazing proofs, in game theory. This, I simply don't even know how he came up with the idea to do this. Now that I see how it's working, of course, it sheds light on some intuition, but still, to me, it's like a mysterious way of doing things where everything can be proven and comes together, but I don't know. I wonder how the basic intuition came. I never, I don't know, is there anything about this? Maybe somebody knows, I don't know. So basically it's not a question, it's just my own admiration for this proof.
I find this proof much less tricky than the previous one that I...
Yeah, but it uses the previous one as a black box. So in that sense, it's true. But the fact to translate it back, to me, this is really, I think for the alternative move games that you have to go down or go up in the oral hierarchy, this is something I think people expected a little bit before based on earlier proofs. But to me, this is coming out of nothing. But actually, I don't know much about it. So probably there are people here who know a lot more about this, how the idea came to translate that simultaneous move game into an alternating move game. This is...
Yes, I think there are several ideas here. One is that just to look at continuation payoffs and construct it somehow, glue everything together, but the conditions are very local. You have at any position, you look at the continuation, and you want all these continuations to glue together. That's one idea. And another thing is that you can, even though the game is finite, when you go to the number of alternatives is finite. When you go to the auxiliary game, you have a much richer space of the moves are zero-sum games, which is a continuum of an element of a continuum. So it gives you a lot of room to do clever things. But I too, I don't. I think there are versions, or there were previous versions, I haven't seen them, of this proof or maybe simpler proofs in the case where the payoff function is just 0 and 1. So maybe simpler proofs can give more intuition. I'm not sure.
I mean, what I also find puzzling is that the randomization has seemed to disappear, right? Because in the original game, you maybe need to randomize, right? If you, I don't know, if you play matching pennies all the time and you take an average payoff or something, or limb soup. While now here in this construction of the transform game, they seem to play pure strategies, right?
Of the...
You know, these A's, they are just actions, right? If I'm not, or action profiles.
Yes. In the auxiliary game, they play pure actions, but the actions themselves, they have a continuum nature. So they come from a similar domain as behavior strategy.
No, it's true that the H's, right? They are from the continuum, but the A's, aren't they? They're just the original.
There is an asymmetry in the Blackwell game. It's symmetric. The two players have similar roles, but in the auxiliary games, again, it's not symmetric. There is you can think of it as a prover and a verifier. One player tries to prove that the value is above a certain level, and the other one tries to...
Yes, so what I wanted to say is that it's puzzling that you don't need player 2 to allow player 2 to randomize, right?
That's true. Yes, it is puzzling. I agree.
I think I have some maybe intuition why this is the case, but it might be super wrong. So I think that it might be best to think of this as not player 1 and 2 of the original game, but two different ones. Player 1 wants to verify that the game has sufficiently high value. Player 2 wants to prove them wrong. And so in the start, player 1 says, this is the value of the game at least. There are 2 things, I don't believe you. How should this work? Player 1 tells you that's the continuation value. And there's always a way that the player 1 can promise higher and higher continuation values. And then player 2 picks a step and says, I don't think this value, you have to choose an overly high value there. And then player 1 says, no, I can do this again. And then you get a long sequence, and player 2 wins if the sequence basically is over-promising because it's not the continuation value, but it's larger than f. And I think what's the tough thing is, if player 2 has a winning strategy, it kind of means what player does is wrong. There must be somehow a higher value that player 2 can achieve, but it doesn't tell very easily what it is. And so I think that what player 2 kind of does is player 2 knows that player 1 has to overpromise, no matter what kind of strategy player 2 uses. But then player 2 can ask, what's kind of the worst up to epsilon strategy the player 1 can use? And then knows even the continuation value there must be overpromising. So player 2, this allows then a strategy in the original game to be constructed that employs this kind of over-promising.
Yeah.
And this verification, of course, that the continuation value cannot be that high. You just have to show it cannot be as high as long as some pass. And this pass you can always choose deterministically.
Yes.
Yeah, this is really nice wording. I find this wording really helpful, Michael. Thanks.
Elon, I have a question for you. Are you aware of a different proof where both sides of the proof use something similar to the one that I used for player 1?
No, I'm aware of Martin's proof. I am not aware of others.
Because I think that the side of player 1 is more intuitive.
Yeah.
You have continuation payoffs, you just play optimally according to these continuation payoffs and you hope for the best. And for the other player, there is a certain trick. You have to apply a certain trick. So I wonder if you could somehow do the same thing for both players, or you really need to do this.
I know.
Okay, anyhow, it's something that we have to get used to. Yeah, another intuition is that an alternate move game is just an infinite formula with infinite number of with a sequence of quantifiers. Yes, player 1 plays the existential quantifier and player 2 the universal quantifier. And they alternate infinitely many times. And in the end, there is a Borel predicate. And the theorem says that the negation of one formula is what you would think should be the negation. You just alternate all the quantifiers and negate the predicate. This is Martin's theorem. So in a sense, you have to construct the formula that says that the value is above you, or something like that. This is the auxiliary game. It's the formula that says that the value is above you. This is some well, that's all I can say. It puzzles me as well. I have no idea. Okay, thank you very much.
Thank you.
Thanks, Ron.
Thank you, Ron.
Thanks.
Thanks.